Welcome back to talking about squares. Um, this is, I'm hoping, probably, it's pretty likely where your brain went next. Your job before coming to this video was to try and find more squares, and I hope you were able to. A lot of people realize that, hey, if I can go across one diagonal like that, which we definitely know is not size 1, we know it's size square root of 2, but it's one diagonal is sometimes how we think of it. I can draw a square then that goes across 2 diagonals. And I drew that purple square here, and I wanted to make sure we were still clear on how I'm finding the area of these. So what's happening is, as I cut it like that, because I need to focus on the vertical and horizontal distances for base and height for area, I can think of this as a big, one of the things to recall is that this really is a square out here, right? This would be a 2 by 2 square. That's a standard square, and that would have an area of 4, which would make 4 the perfect square, and square root of 4 is 2, and hopefully that stuff's starting to fit together in your brains now. But if you recall, and you talked about this a little bit with your MOOC shape, and you certainly learned about this in 7th grade and the years before, a triangle is always half of its square or rectangle, right? So if this square is 4, that's how I know this triangle right here was 2. And that's how I knew it would be 2, 4, 6, 8. And so then I could fill in my chart that the area was 8. But then again, what's the side length? The side length is not going to be a nice even number because 8 is not on our list of perfect squares. So once again, to recap from before, these are called perfect squares. And they are perfect squares because when you square root them, they give you a nice whole number, okay? So this here, if I see the number 8 on here, I know it's a perfect square, but 8 falls in between those perfect squares. 4 jumps directly to 9. There are no perfect squares in between those. So 8 must not be a perfect square. So I put that on my chart here, and I said, okay, this area was an area of 8. And its side length, I'm going to write square root of 8. And I'm going to show you when I type it in my calculator. Remember, let's refresh our memories how to do this too. Square root of 8. So I did second x squared 8. Okay? Watch what kind of answer I'm going to get. Not a nice even number. This has a name. Okay? What I see is I see my calculator screen is full. And what that means is that this number does not terminate. This decimal does not terminate. Beyond that, I can also see that this decimal doesn't repeat. There's no pattern, and it never ends, just like pi. Now, before I give you the name of those, I want to show you some more squares that I found, and you can see if you found these as well. Some of you, I know I'll see that when you took your picture on these notes, some of you definitely found these squares. So if you look here, I did a little nesting thing again. The nesting thing is handy when you're trying to see how many can I fit. And the nesting thing is also really helpful to find these areas, because watch this. So this is the same red one we had over here with an area of 2. This is the one with an area of 8. Here's another way I know it has an area of 8 is because now actually this red one is just repeated all the way down. Watch if I draw these dashed lines here to break this apart. Here's another way you can look at the areas of these. This red one is area of 2 with a side length of square root of 2. This purple one is an area of 8 because look, 2, 4, 6, 8 with a side length of square root of 8. This green one, if you didn't find this one, make sure you get this one drawn. This one has an area of 2, 4, 6, 8, 10, 12, 14, 16, 18 with a side length of square root of 18 because again, is 18 on my list of perfect squares? No, that means it's a unique square. We haven't found that one yet. And again, and here's the biggest one, it was 32. Again, when I typed that in my calculator, if I do square root of 18, here's how I know for sure that 18 is not a perfect square. If you type it in your calculator and you get this big, long, non-repeating, non-terminating decimal, you know you don't have a perfect square. Watch what happens when I type in one of these perfect squares like 49, square root of 49. You can still totally type it in the computer or the calculator, and you get a nice whole rational number, okay? That's because 49 is a perfect square, whereas 32 is not. Now, these kind of numbers that we're getting when we square root these things, these numbers are fascinating, and they took time in our history to discover them, but it was a huge discovery and an important one that allows us to do all kinds of mathematics that we couldn't do before. And this is a new group of numbers for you in your 8th grade number system strand. So these kind of values that I got from this nesting picture, these kind of values are they're non-perfect squares. These are perfect squares, you square root them and you get a nice rational number. These are non-perfect squares, and when you square root them, you get what we call an irrational number. And we're going to clarify that with our solidifying notes next week, but these are called irrational numbers. And we're going to talk about and clear up a lot more how you recognize them. But the main purpose of this goal in 8th grade and looking at all these squares, and often we call these are your normal straight up and down squares that give us our perfect squares. These are sometimes called tilted squares. They're still squares, but they've been tilted, and it makes things a lot more complicated because now I can't just count the side length because it's not one, it's not the same distance. So you may have found some of those. I know some of you found some other ones too, because what you can start doing is you can start tilting things in a different way. It doesn't just have to be up 1 over 1. You can do different kinds of tilts in your squares. And I'm going to show you one more, and then I'll let you spend today trying to get some more of them, okay? So let's say I start on this peg right here, all right? I am going to move like this. Are you ready? I'm going to go up 1 over 2 to that peg there. See what I did there? I didn't start moving until I started counting. Remember, you're counting spaces and not the dots, okay? So that, like a ruler, this goes up 1 over 2. And then I'm going to connect right from that dot to that dot. Okay, now that's a certain distance. Now you ready for this part? Follow along, okay? I'm going to turn my page 90 degrees so that it's on the side like this. This is how I'm going to make sure I get a square. And then I'm going to start where I left off, and I'm going to do the exact same movement. I'm going to go up 1 over 2. And I'm going to connect to that dot. Now I'm going to rotate my page so that it's upside down. Twist it so that it's upside down, and I'm going to do that movement one more time. I'm going to go up 1 over 2. Now this is a moment where often students in class say, wait, will you show me that again? Here's the nice thing about the video: pause it, rewind, watch it again. It can be a little tricky to draw these squares. And then I just connect here. Some of you already came up with this one. Some people that come up with this one then get a little stumped on how to find the area and the side length. They know it's a unique square, but they're not sure where to go from there. So let me show you how we do this. Again, it goes back to some of the things we were doing with MOOP and messing around that way. Watch this, okay? If I do that movement, remember I went up 1 over 2, and that's how I started. If I flip that up 1 over 2 movement inside, and I think of this as an up 1 over 2, I'm going to do the dotted. I think of this as just a 1 by 2 rectangle. That movement created the dimensions of my rectangle. So this goes up 1 over 2. Now the rectangle then would be a 1 by 2 rectangle, right? And the area would be 2 squares. And what do we know about triangles? The triangles are half of it. So half of 2 means this triangle has an area of 1. Okay? And I have those same triangles all the way around. Imagine everywhere you did an up 1 over 2 movement, there's a rectangle there. Here's your up 1 over 2 movement. Here's another rectangle there, but I'm of course only really concerned about half the rectangle because that's the part that's actually inside my square, and that's what I consider with area. And then you have one more up 1 over 2 here. The triangles are half of those 1 by 2 rectangles. Say that one more time. The triangles are half of those 1 by 2 rectangles. And then I know I have one more square in the middle. That's a full square. Put it all together, and I'll let you guys go back and fill this in your chart to get some more values. The area of this square is 5. Now let me ask you that. Is this unique? Have we found an area of 5 yet? Well, go back to your chart and look. Have we found an area of 5 yet? We certainly have not. We just found a unique square, another one. And I drew that on grid 5. The area of that square was 5. Is this on my list of perfect squares? No, it is not. So guess what my side length is? square root of 5. Now I'm also going to write off to the side here so that you see how it goes together. If I do square root of 5, and we'll practice this a lot more as we move forward, and I get this decimal here, one of the things we do in math is we use a notation. Square root of 5 doesn't have an exact answer. That's what's so crazy about these irrational numbers. There is no exact answer for square root of 5 except for square root of 5. This is what we call exact form. But I can write this. I can write this is approximately, not equals. You make it a squiggle in math when it's approximately. I can't possibly write the whole thing. I could write everything my calculator shows me, and that's still not the whole thing. The calculator just ran out of room. But I can approximate it and round it off and say this is approximately 2.24. That's about what the side length is. It's officially exactly square root of 5. It's approximately 2.24. Okay, that's a decimal approximation. Now, I'm going to let you guys try and find a few more, but first I'm going to show you one more example because finding this area, sometimes we get a little thrown off by that. I'm going to go over to grid 6, and you know what this means is if I can go up 1 over 2, I can also go up 1 over 3, up 1 over 4, up 1 over 5, and then I'm going to get unique squares every time I do that, okay? I'm going to show you one more that actually goes, what if I start here, and I go up 2. Now, if I go up 2 over 2, you should realize quickly that that's actually a square we already have. Up 2 over 2 is actually this purple square right here. That would not be unique. We already have that. We already have everything that goes up 1 over 1, up 2 over 2, up 3 over 3. We already have all of those. But I can go up 2 over 3. Ready? I'm not going to start counting until I start moving. Here I go. 1, 2, 3. I land right there. And now I can, and some people like to use a ruler to get these nice and straight. That's just fine. So I just went up 2 over 3. Now I'm going to twist my paper this way, and I'm going to go that exact same movement, up 2 over 3. Okay, and then I'm going to twist upside down. Ready? I'm upside down now. What movement am I doing? Up 2 over 3. Here I go. Up 2 over 3. And I'm going to connect here and here. I just made another unique square. And watch me find the area of it. You ready? I went up 2 over 3. So here's the like rectangle movement, right? I'm going to flip that inside. I'm going to flip that inside. The overall rectangle would be 2 by 3. 2 by 3 is 6. Remember, I only want the triangle part that's actually in my square, so that's half of it. So half of 6 is 3. That means the area of that triangle right there is 3. Here's the other 2 by 3 movement. I flip it inside. Here's my 2 by 3 rectangle. That's 3. Sometimes when we just think of it as the triangle, we get confused on how to draw it. Think of it as this overall rectangle to help you draw it. Here's my other 2 by 3. So that finishes it off right there. And again, you can pause these and rewatch these anytime you need to, because this can be a little tricky. And 2 by 3 here. And I have 1 square in the middle again. Sometimes you won't just have 1 in the middle. Sometimes after you draw those rectangles, and you'll see as you work through, I'll show you, I'm going to let you try and then I'll show you some. But sometimes you end up with a bigger square in the middle, but I always draw those outside triangles first and then see what happens in the middle. Don't try to make the middle square happen first. That gets confusing. So 3, 6, 9, 12, 13. The area of this square is 13. Is that on my perfect square list? No, it is not. And it's not on anything we found so far either. So it is absolutely a unique square. And because it's not a perfect square, that means the side length is going to be an irrational number. And it's going to be, this is how I write it exactly, square root of 13. And then I can type it in my calculator, square root of 13, and I can say it's approximately 3.6. It says 605, so the 5 rounds that up to 3.61. Okay, you guys are going to pause the video right now, and I want you to see if you can get, you have maybe 3 more grids, 4 more grids. I don't know, try and draw 3 or 4 more squares. If you can find their area and their side lengths, try to get a little more of your chart filled in. Remember, you can try things like make sure they are unique squares. In fact, if you go up 2/4, is that going to be unique? It'll be this one going a little bit bigger. So it will be. It'll follow this same kind of tilt pattern. It'll just be a larger one. So you can do that. You can start going up 1/3. You can go up 1/4. So try to get 3 or 4 more squares drawn on here. See if you can find the area, and so that you can get 3 or 4 more spots filled in on here. Pause the video, draw a few more squares, and then we'll see how you did. Okay, I'm excited to see your pictures of your notes so I can see what you're drawing and what you're coming up with. But I am going to share with you a few more. And if you're like, I only came up with 1 more or 2 more, that's okay. Write some more of them down right now. So I have a bunch drawn. Again, feel free to pause or look at whatever you need to. But here's some more examples. Here's the up 1/2. Here's the up 1/3. Here's the up 1/4. So there's some more examples there. And this is what I meant by you won't always get a 1x1 square inside. So when I drew this one and I went up 1/3 and I drew my 1x3 triangle, 1x3, 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 when I drew those triangles, I ended up with a 2x2 square in the middle. So watch for that. In fact, as I keep going up 1 over more, interestingly enough, look at these numbers that end up inside. 1, 4, 9, 16, 25. Some really interesting math patterns happening here. But the overall areas ended up as, so this is up 1/5. I got this square of 16 in the middle, and this is 2.5 plus 2.5 is 5. So 5, 10. This one was an area of 26, which gave me a side length of square root of 26, approximately 5.1. Okay, here's up 1/6, up 1/7. A few more if you decided to go not up 1, okay? And again, pause on any of these that you need to if you want to write them down. You can go up 2/4, looks like that. You can go up 2/5. And you can keep going, up 2/6. This is a really fun one right here. Some people go, I went up 3/4 and I got this unique square. Surprise, this one is actually not a unique square, because look at the area that you get. The area is 25, which means the side length is 5. That's actually not a unique square. It's the same. It's kind of crazy. If you don't believe me, I'll show you. If we have our little measuring tool here, remember this was, I don't know where I put it, so I'll make a new one. Oh yeah, it's right here. See how this is actually 1, 2, 3, 4. I'm gonna mark one more. This is a distance of 5 because this is like 0 on a ruler. So you don't start counting, you don't count this one, you count as you move, right? So this is 1, 2, 3, 4, 5. Don't start counting until they start moving, and watch what happens when I bring that over here. It really is a side length of 5. So that one is actually a tilted square, but it's not unique. So that's interesting, and we'll learn some more why about how that's working out later. For now, the main point of this, I hope you got some squares drawn, and I hope you got this good vocab on here. The main point of this, and we're going to solidify this some more with some notes next week, but the main point of this idea is understanding the difference between rational and irrational. That's what we're really going to focus on next week. But also this idea of if you take a perfect square and you square root a perfect square, you're going to get a nice rational number. If you take a non-perfect square and square root it, that's one of the times that you get this new type of number called irrational. And it's going to make it possible for us to do all kinds of really useful mathematics as we move forward. So take a picture of your notes, move on to the practice, and we'll learn more about this next week.